Hello and welcome back. The following problem states, determine the rate law and rate constant for the following hypothetical reaction. In addition to providing us with the generic reaction equation, they also provide us a table with 3 different experiments at different concentrations of A and B and the initial rates. In order to approach this problem, there's a few things that we're going to do. I'm going to go ahead and write out the generic rate law for this problem. We're going to walk through on how to kind of solve it. Well, in order to actually solve for any of the coefficients, we're going to have to hold 2 of these experiments constant at concentrations of either A and B in order to solve for the other one. Let's go ahead and vary the concentration of A and keep the concentration of B constant. We're going to do this for experiment 1 and experiment 2. I'm going to divide everything by the second experiment, rate 2. Oh, actually, I'm going to do 2 over 1. Go ahead and do 2 over 1. In experiment 1, we'll have as followed, divided by everything from experiment 2. Okay, once we've done that, well, if we're holding constant concentration of B, well, this cancels out. Rate constant does not change, so this also cancels out. And so we're left with rate 2 is equal to the concentration of A for the second trial, held to the exponent m, rate of the first trial. Rate 2 over rate 1 is equal to concentration of A for the second trial over the concentration of A for the first trial. Well, in order to solve this, we go ahead and we plug in the appropriate values. We get 4.2 times 10 to the negative 4th divided by 2.1 times 10 to the negative 4 is equal to 0.20 divided by 0.10 molar. We have our subscript. And this ends up simplifying down to 2 is equal to 2m. Well, the way that we would typically solve for m is you take the natural log of each side. And so let's go ahead and do that. We'll take the natural log of each side. Once we do that, this simplifies down to ln of 2 is equal to m ln of 2. We divide each side by ln of 2. And m is equal to 1. Well, we're going to go ahead and do the same exact steps, but for looking at the concentration, but looking for the value of n for B. But in this case, instead of holding constant concentration of B, we're going to hold constant concentration of A for the second part. The same thing's going to happen over here. Once we hold everything constant, and so for this case, we're going to look at experiments 1 and 3. And we're going to have the experiment 3 on top divided by experiment 1. In this case, concentration of A is being held constant, so it cancels out. We're left with a similar expression down below. And we do the same thing. So for rate 3, it was 8.4 times 10 to the negative 4th molarity per second divided by 2.1 times 10 to the negative 4th molarity per second is equal to the concentration 0.030 molarity to N divided by 0.015 molar held to N. And this is going to simplify down to 4 is equal to 2N. We'll do the same thing. We'll take the natural log of each side, and this will simplify down to natural log of 4 is equal to the natural log of N. The exponent comes out of 2. Divide each side by ln of 2, ln of 2, and we get N is equal to 2 in this case. So we had M was equal to 1, and N is equal to 2. When we go ahead and write this into our rate law, so rate is equal to K times A, which is 1, B is to second order. We can go ahead and solve for K by rearranging this rate law by saying K is equal to rate over A and B to the second power. We can go ahead and plug in any of the experiments into this expression, and once you do that, you get K is equal to 9.31 over molarity seconds squared. Oh, sorry. Molarity squared per seconds. And you can use any of the following experimental data to plug into this value.